actually, and I was going to speak about something that Jethro is speaking, and yeah, I didn't come up with anything meaningful, and I got tired that I've been giving talks about chiral homology for the last 5 years. So it's probably fun to give a talk about something that I'm not really comfortable with. So I'm quite sure that this talk would be given in a very different way by my collaborators. So this is joint work with Luis Alvarez Consul. Oops, like this, Consul, and David Fernandez. And a version without Luis is in the archive already, and I'm not sure how much I'm going to have time to talk about this double stuff. I'm mostly going to be hand-waving a very old story, which is a diagram that I'm quite happy to explore, and I've been talking about this diagram for many years, but I've never done anything useful. So let's start with a very basic observation. Let's say that you have a Poisson algebra. But let's put some conditions on this Poisson algebra. So this is, say, an algebra P over a field K. And let's suppose that it's graded. Thank you, Tomoyuki. So let's suppose that this is graded by the positive integer numbers. And let's suppose that the multiplication is actually graded of degree 0. But let's suppose that the Poisson bracket is graded of degree -1. So this is something that happens quite often. And the question is, let's study this structure. So some geometric structure emerges from this description. You quickly realize that this data can be packed, at least a piece of this can be packed in the following. So P0, let me call this guy O, is a commutative algebra. Well, just the degree 0 piece is preserved here. If you put P and Q equal to 0, the multiplication preserves this, the unit is there, and this is just a commutative associative algebra over K. Commutative algebra and associative and unital over your ground field K. P1, let me call this guy E. This guy is now a Lie algebra. Is an O module. So this is the case here. When you put P is equal to 0 and Q is equal to 1, it lands back in Q is equal to 1. So this is P is equal to 0, Q is equal to 1 in those requirements. But it's also a Lie algebra over K. This is the case P is equal to 1 and Q is equal to 1 in this identity here. If you grab something in P1 and take the bracket with something in P1, you land in P1. And moreover, I should probably continue here, P1 acts on O by derivations. If you grab something here and something here, you can send it to their Poisson bracket, which lives in here. So this is again the case P is equal to 1, Q is equal to 0. And let's put names here because let me say A and B. In B. And I can just denote this as A acting on F. And now the Leibniz rule, since I started with a Poisson algebra, the Leibniz rule says that, is it me or this is having some feedback? I don't know from where. Probably I'm just too loud. Anyway, the Leibniz rule in P says that A acting on Fg is equal to AF times G plus F AG. So that means that this object here is a derivation. So what you get is a map from E into derivations over K of O. Moreover, this E has a Lie algebra structure given by this bracket, and you just check that this map here, by the Jacobi identity, for the Poisson bracket in P says that this is a Lie algebra morphism. It's a Lie algebra morphism. Okay. So here you have the Lie bracket coming from the Poisson bracket on P, and here you have the Lie bracket of derivations, of vector fields. And this is preserved. Both are Lie algebras over K. They're not O-linear Lie algebras. And this data, all of this data is compatible in a way. The compatibility is still going to be an example of the Leibniz rule. This feedback is nasty. Let me just put this down. Probably here it's going to be better. Come on. Let's try that. Hopefully there's less. Sorry? Oh, you don't think it's feedback? Yeah. Anyways, so this was using Leibniz for taking the bracket with respect to the product of two things. So now there's the following compatibility of, well, we have three structures here. We have an O module structure on E, we have the Lie bracket on E, and we have the action of E on O. And they are compatible in the following way. The Lie bracket of A with FB. Here, A and B are in E, and F is in O. Well, this is not, the bracket in E is not O-linear. This is A acting on F times B plus F times the bracket of A and B. Okay, so the statement is that from a Poisson vertex algebra, a graded, from a Poisson algebra, I'm just going ahead, from a Poisson algebra, which has a couple of more adjectives, so it's graded, and is of degree -1, so the multiplication is always of degree 0, and I'm requiring the Poisson bracket to be of degree -1, so this degree -1 meaning the Poisson bracket is of degree -1, I went to the notion of a Lie algebroid. And a Lie algebroid is that datum, is a commutative algebra, a Lie algebra, which is an O module that acts on the commutative algebra by derivations, and it satisfies this compatibility condition. So this is known as a Lie algebroid. The algebraists know it as, I think differential geometers would say this is a Lie-Reinhardt algebra. I would call this a Lie algebroid. In differential geometry, you would require that this guy is a projective module over O, which is finitely generated. Okay, so that's a functor from Poisson algebras to Lie algebroids. You can do this smoothly if your Poisson algebra, if the P0 you take the spectrum of that, you get a sheaf of commutative algebras over somewhere, and if this guy becomes a sheaf of modules over this, then you can describe this in the usual case of a variety, a vector bundle with some connection, and a map to the tangent space, to the tangent bundle of your variety. I won't care about these subtleties. But the thing is that up to which point this can be made into an equivalence, well, how do I go back from here to here? So if you give me something like this, what I could try to do is take the symmetric algebra of E over O and try to put a Poisson bracket there. And it's easy to construct the Poisson bracket there. You just declare that the bracket of E happens in degree 1. The bracket of something in E with something in 0 is what happens, is the action. And then you just extend by the Leibniz rule, and this gives, on this P, a structure of a Poisson algebra, which is graded and the degree is -1. And if you start with a Poisson algebra and you go this way, you get a quotient of your original one. So what happens is that if this Poisson algebra is, well, this is false. This statement is false. If this Poisson algebra was generated by whatever happened in degree 1, then this is actually a quotient. And if it's freely generated by what happens in degree 1, then this is an isomorphism. So this is the free Poisson algebra generated by E over O. So in that sense, that's an equivalence. Okay, so we spent some time on that. Let me do the Poisson vertex algebra version of that, even though probably everyone in this room already knows that. But I find that construction nice. So I'm not sure if everyone knows what a Poisson vertex algebra is. So let me give you a couple of definitions. So definition. A Lie conformal algebra is a K of del module, let's say R, together with, so this is going to play the role of Lie bracket in the Current world, together with an operation, R tensor R, to polynomials in a formal variable lambda, that I will denote A tensor B maps to the bracket of B. So this is just a polynomial, Cn lambda to the n. This sum is finite. I think people typically normalize this like this. But the whole point is that these Cn's are in R, satisfying a couple of axioms. So first of all, so that's easy to see. This one is a little trickier. So this means take the bracket of these two, you get a polynomial in lambda with coefficients in R. Now to each one of the coefficients apply, so multiply them by lambda, you still get a polynomial, and then also apply del to those coefficients. So these are called sesquilinearity. And this is just encoding the fact that this is a C of del module, this is a C of del module, or a K of del module. The tensor product is a K of del module because K of del is a Hopf algebra, so del acts on the tensor product naturally. And this thing here is also K of del module in a non-trivial way. The K of del module structure here is given by del acting here, a multiplication by lambda there. So this is saying that this map is a map of K of del modules. So this is just as simple as that. This is this condition here. Skew symmetry is slightly trickier. This says that if you want to compute B lambda A, then this thing is, well, I would usually put A, B here, some bracket of A and B, but then what we'll do is we're going to put minus del minus lambda. This one is slightly trickier to see. What's going on here is you compute this is a polynomial on a formal variable. Now change that formal variable to minus lambda minus del and apply del to the coefficients. So that's what this identity says. And finally, the Jacobi, or probably you can just write Jacobi here, and the Jacobi condition. This says that A lambda B mu C Well, A lambda something, the bracket by something, the adjoint action should be a derivation of the bracket. So this is A lambda B, lambda plus mu, C, plus B mu, A lambda C. So this, both sides are an equivalence, are an equality here on R polynomials in lambda and mu. So this is where that equality is happening. So that's a Lie conformal algebra. And infinite dimensional Lie algebras give rise to these guys. So examples of this. Guess I'll give one. So one example of this is the Virasoro Lie conformal algebra. This is R is freely generated by one guy as a K of del module. And then there's a central element that gets killed by that. So I need to tell you what are the brackets between the generators, and the bracket of L with itself is del L plus 2 lambda L plus lambda cubed over 12 times C. And the bracket of L with C is equal to the bracket of C with C, which is equal to C. And that's the unique, well, that's essentially the unique, there's one extra case, Lie conformal algebra, which is generated by one element, is a central extension of something that is generated by one element. If you put C is equal to 0 here, you get a Lie conformal algebra as well. And that Lie conformal algebra has a central extension, which is what I've written here. So this is essentially the unique, non-trivial rank 1 Lie conformal algebra. Of course, I haven't given you the brackets for arbitrary elements, but arbitrary elements can be written by sesquilinearity. They are polynomials in lambda, in del applied to L. Okay, so that's a Lie conformal algebra. Now, definition. A Poisson vertex algebra well, this is the datum of, now I'm going to switch to A instead of R, a product, a unit, and a bracket. Such that, yeah, so let me explicitly add to this list the action of del. So what I want is that A with the bracket and del is a Lie conformal algebra. I would want that with the product is a unital associative commutative algebra with a derivation. So we'll require that A dot with the unit and del is a unital commutative associative algebra. And well, this is essentially the definition of Poisson algebra. I've given you a Lie algebra structure, a commutative algebra structure on the same guy. Here I want a derivation. With del is a derivation. And now you just add the Leibniz rule. So a compatibility between these two structures is that the bracket with the product, the adjoint action is a derivation. So this is just A lambda B times C plus B times A lambda C. So examples of Poisson vertex algebras, for anyone that was there last week, a couple of weeks ago at IMPA, we've been starting from a vertex algebra. So if V is a vertex algebra, it comes naturally with a filtration. And the associated graded is a Poisson vertex algebra. Which is a singular support of V or the classical limit of V. So Poisson vertex algebras from this perspective are classical limits, are associated graded of vertex algebras, which are some non-commutative objects that I get to view them as commutative objects on the associated graded, in as much as this guy here, if I take O to be just the field K, E to be just a Lie algebra, this thing is the associated graded of the universal enveloping algebra of E. This thing makes sense even when O is not the field K. You have the algebra of differential operators associated to a Lie algebroid, and its filtered algebra is an associative algebra which is filtered, and the associated graded is this guy, is this Poisson algebra. So this is really the picture that I want to have, that vertex algebras are like the universal enveloping algebra of a Lie algebroid, and Poisson vertex algebras are the associated graded of those. So they look like the symmetric algebra of the Lie algebroid. So the question is, what is the Lie algebroid? So when I started with a Poisson algebra, or from this perspective, the symmetric algebra of something, well, I'm taking something that is freely generated by E, and this E had a geometric structure in itself. It was a Lie algebra, and it was compatible with the commutative algebra no. So you can ask the same question for a Poisson vertex algebra. And actually, I can just remove that board. So I think I'm going to spend most of my talk just describing the very old picture. I think it's a nice picture. So now let's look at the grading. So I didn't take arbitrary Poisson algebras. I took Poisson algebras that were generated in degree 0 and 1. And I required that the Lie bracket was a particular degree. So now I'm going to look at a Poisson vertex algebra. Let's say that A is a Poisson vertex algebra. So let me just use PVA. I will require some gradings. So I'll put that A is a direct sum of AN. N is bigger or equal than 0. And, well, let's require that the product is of degree 0, just as before. Oops. But let's require that the lambda bracket, the Lie bracket, is of degree -1. And here I need to be slightly more careful. So this guy, if you give me A in AP and B in AQ, it would send it to their bracket. And what I will require is that this Cn lives in A, P plus Q minus N. If I write this, this would be naturally considered to be a bracket of degree 0. So I'm going to write the -1. So this -1 here is the analog of the Poisson bracket being of degree -1. And I didn't say so, and I'm actually now not sure if this comes for free. So I'm just going to add it, just in case. But del is going to be of degree 1. This, of course, happens in this situation. So if you have a vertex algebra, it comes with a naturally decreasing filtration. The associated graded is a Poisson vertex algebra, and this Poisson vertex algebra satisfies all of these conditions. So it's graded in that sense. All right. So given such a Poisson vertex algebra, I'm going to ask this very same thing that I did for Poisson algebras. What is it there in degree 0, and what do you find in degree 1? And this is something that surprisingly was studied in geometry way earlier than vertex algebras were there, or even Poisson vertex algebras were there. So this is something that has been studied in Poisson geometry for a long time, which is the notion of a current algebroid slightly generalized. So now we know them as current Dorfmen algebras or weak current Dorfmen algebras, but this has been in the literature for over 30 years, 40 years now. So let's A be such a Poisson vertex algebra. And from now on, when I say Poisson vertex algebra, I mean with a compatible gradient like this. So of degree -1. Then O, which is A naught, is a commutative associative algebra, and unital. The multiplication preserves it, and there's nothing for the bracket. If I take two things in degree 0, the lambda bracket doesn't give me anything new, okay? Because I don't have anything in degree -1. What happens in degree 1? So let's take my E to be whatever I have in degree 1. And this is, first of all, this is a module. It's an O module. Because of the multiplication preserves degree. So it is an O module. Second, now I can look at what is the lambda bracket, and now it's non-trivial. The lambda bracket of something in E with something in O is going to land in O. So I have a map from E tensor O to O, which grabs something here, and it gives me the lambda bracket. Let's use a different letter for B instead of, let me use F, as if they were functions. So if I take the lambda bracket, by the gradient condition, this thing is equal to its constant term. There cannot be a power of lambda there. And this is an element in O. So I'm going to denote it by A acting on F. So I have an action of E on O, and by the Leibniz rule, this action is by derivations. That is, I have a map from E to the derivations of O. Over K. Or equivalently, I have a map from omega 1 of O to E. This is a map of O modules. Okay, so we've analyzed the product on O, the product of O with E, the bracket of O with E. If I take the product of E with E, then I land away from degree 0 and 1, which is what I want to analyze. So I'm not going to take the product of E with E, but I'm still left with the bracket of E with E. And the bracket of E with E, this is a new feature that appears in Poisson vertex algebras, but wasn't there in vertex algebras, in Poisson algebras, is that if I grab E and I look at E and I take the lambda bracket, then I land in E plus O. Let me give you these two maps. So I'm going to grab A, I'm going to grab B, I'm going to take the lambda bracket of A with B. And this has two components. The first component is in E, and I'm going to denote it with a bracket. So this is defining the right-hand side. Plus. And the second component is in O. So this is defined by this formula. It's the coefficient of lambda in the lambda bracket of these two guys. So this is in E, and this is in O. So I have these two maps from E tensor E to E, and this is going to be like a Lie bracket, an honest Lie bracket in this guy, almost. And this is going to be a pairing from E tensor E into my algebra O. So what are the axioms that you get out of the Poisson vertex algebra? So the Poisson vertex algebra lambda bracket was a Lie conformal algebra. It satisfies Skew symmetry, and it satisfies the Jacobi condition. So out of those, you will get a bunch of axioms. So this bracket wants to be a Lie bracket. So what does it mean it wants to be a Lie bracket? Well, the adjoint action is a derivation of that bracket. And indeed it is. So this form of the Jacobi condition is true. So this is satisfied. I cannot call it Jacobi because this guy is not skew symmetric. So A bracket B plus B bracket A is not 0, but it fails to be 0 by the pairing. If you remember, skew symmetry on the Poisson vertex algebra is going to change the order of these two guys, but replace lambda by lambda plus del. That del is what it's going to appear here. It's going to appear the derivative of the pairing. So del here measures how much this bracket is non-skew symmetric. Okay, so let's place a little game more. So now I can look at the Jacobi condition for this bracket and analyze and the skew symmetry condition for this bracket. So the skew symmetry condition, I've used it here, but I also get that this guy is symmetric. AB is equal to BA. And I get a few things more. Let me tell you some of them. So the bracket, for example, a relation between the bracket and the pairing. A, B, C. I might get this wrong. So typically, you would get, let me see how I'm going to write this. So I think I want to write this way. So if you do B with AC, you would say that the pairing is invariant if this is 0, but this fails to be 0. And this fails by D of something that, of course, I'm going to forget what it is. So I suppose that this is probably the action of A on BC. That I think is correct. I don't want to even waste your time and my time checking whether that's what appears on the other side. But the point is that you get something that is new, that it's because of the action by the derivations. So the pairing is not invariant for this Lie bracket. And then, what else am I missing? I think I'm missing just the following one, that del A, del B, del F, del G. Is equal to 0. All right, so this gadget is known as a Current Dorfmen algebra. So the datum, and more than just writing axioms, it's better to give you an example, because these are all examples. The datum of your commutative algebra, just ring of functions on a manifold. Your O module, just some vector bundle on that manifold. The pairing, so this vector bundle comes with a metric. The Lie bracket and the derivation satisfying these axioms is known as a Current Dorfmen algebra. It's called a Current Dorfmen algebra. So current algebroids are this, where people require that this pairing is non-degenerate. This didn't appear at all in our analysis. The point is that if you have a Poisson vertex algebra and you take the first 2 degrees, you get this gadget. And this gadget was studied since Dorfmen, and because in her analysis of Dirac structures, because we have a canonical example of this. Should have given you a canonical example of Poisson algebra, but well, or of Lie algebroid. But here we have a canonical example of both canonical examples. Well, of a Lie algebroid. What is a Lie algebroid? If you have O is your commutative algebra, then the derivations of O is canonically a Lie algebroid. This guy comes with the Lie bracket and it acts on O by derivations, by definition. So that thing is a Lie algebroid. And the Poisson algebra that we associated to this Lie algebroid was the symmetric algebra of der of O over O. So this is the algebra of functions on the cotangent bundle of the spectrum of O, which is the canonical example of a Poisson variety. So how about a canonical example of a Courent Dorfmen algebra? So now take O, your commutative algebra, and now look at derivations of O, but add also one forms. So the Kähler differentials of O. This is going to be my E. And I need to give you all the data that satisfies those conditions. So, well, I need to tell you what the bracket of two things here is. So let's take x plus alpha. X is here, y are going to be here, alpha and beta are going to be here. So I need to tell you the bracket and the pairing. Well, the pairing is trivial. This is the dual of this. So by the universal property, this thing here is the same thing as hom from omega 1 to O. So the pairing is just the evaluation map. So this is just alpha of y plus beta of x. Now the bracket is non-trivial. The bracket is the Lie bracket of vector fields. And now I need to add something that is not skew symmetric. Well, vector fields act on forms. So I can just look at this minus. And the other thing I could do is look at this guy here, this form, and act with y on this form. So what I'm going to do is not Ly of alpha, but something similar. I'm going to contract with y d alpha. So exercise check that this satisfies all of these axioms. So that's a canonical example of a Courent Dorfmen algebra. It's the tangent bundle plus the cotangent bundle. And replacing all the structures that you know about derivations of O with its Lie algebra structure by this is what led to, I don't know, a lot of geometry in generalized complex geometry, for example, generalized scalars, manifolds, and so forth. And so I've given you essentially by definition a way of going from Poisson vertex algebras to that gadget. You just look at what happens in degree 0 and degree 1 and you obtain the gadget that was known. The other way around is essentially the same thing. So theorem, there exists an equivalence of categories. Between Courent Dorfmen algebras and Poisson vertex algebras with a bunch of adjectives, which are the ones that I already told you for Poisson algebras. So graded of degree -1, namely the lambda bracket is of degree -1, and freely generated over its degree 0 part by what happens in degree 1. Okay. So, yeah. I just gave you two inverse constructions. Yeah. So this is, I have these two maps, and I'm restricting to whatever the part of the Poisson algebra that I can hit from Poisson vertex algebras. So that's why it's, right. So I have these two adjoint functors if I don't add these adjectives here, like freely generated in degree 1 by whatever it is. So I have an adjunction, which is forget what happens in degree 1, and I have a free Poisson vertex algebra generated by a Current Dorfmen algebra. Yeah, so either two ways of writing the same thing. The freely generated here is the tricky part. To prove that there exists an object that is freely generated by that datum is the hard part. All right, so, but this brings us to a table that I think is nice. And since this is a physics institute, I want to mention that table. So we have Lie algebroids. We have, yeah, this is too large. We have Lie algebroids. We have Poisson algebras. And in my mind, this is classical mechanics. But there's something else that you can do when you have a Lie algebroid. You get a symplectic supermanifold of dimension of degree 1 or of weight 1. I think this has a name. I'm not going to describe what this is. But I'll give you an example. Manifold of degree of weight 1. So this is simply, in this case of the Lie algebroid, I took the symmetric algebra. Let's change names. Since this is closer to differential geometry, let's use the notation that those guys use. So the example there was if I have a Lie algebroid, so this is my E, which is a module over O, then I can think of this as some vector bundle over a manifold M. So these E are the sections of that bundle. And in the canonical example where this vector bundle is the tangent bundle, then the Poisson algebra that I constructed was the algebra of functions in that manifold, in the cotangent bundle of M. So the Poisson algebra, when E is derivations of O, was functions on T star M, where M is the spectrum of O. However, something that we can do is we can shift E. So instead of looking at the tangent bundle, I can shift it and view something like this. This is going to lead to a symplectic manifold, which is going to be the spectrum of this thing. It's a supermanifold. This carries a canonical symplectic structure. The symplectic structure is actually coming from the Poisson bracket now on this guy, which is of degree 1. And this is again an equivalence. If you look at symplectic manifolds of weight 1, so these are symplectic supermanifolds. Again, you look at what happens, what do you have in degree 1, and that is a Lie algebroid. But the interesting thing about this is that this is, well, it's classical mechanics. This is a quantum field theory it's a classical field theory in dimension 0. This thing is the target of a sigma model of dimension 1. So we have Current Orthogonal algebras. So this is one level up. Courent, Dorfmen. I hope that's not mine. Algebras. It might be mine. Current Dorfmen algebras. Here I said it was PVAs. And here you get a symplectic NQ manifold of weight 2. This is actually the work of Reutemann. So that's the only name that I've mentioned so far. Reutenberg, I'm sorry. It's not Reutenberg. It was bad, and I'm on record. So this is Reutenberg. That's the theorem that he proved is that these two things are equivalent. To each such gadget, he associates a super-commutative algebra, the spectrum of which is a manifold that comes with a natural symplectic structure. And the way you construct that is you take essentially something like this, something freely generated by E, but you put it in degree 1, so you declare that to be odd, and that's why this variable is anti-commute. And again, this is the target of a classical field theory in dimension 3. This is what this is known as the Courent sigma model. And this would be something like the Poisson sigma model. So these manifolds are targets, natural targets of classical field theories in different dimensions. So what I would like is to extend this diagram. So how can we extend this table? In which directions can we extend them? Well, one natural direction is this is a Poisson vertex algebras with 0 lambdas. This is a Poisson vertex algebras with 1 lambda. There exist Poisson vertex algebras in any dimension. In any dimension. Both of them, I guess this is just going to be a comment for mostly for physicists, there's something that has this canonical target, which is the AKSZ module. So the AKSZ is just an action that whenever you give me a symplectic supermanifold of weight n, it gives you a sigma model with targets from manifolds of dimension n minus 1. So, I'm sorry, n plus 1. So this is a sigma model from a 3-dimensional manifold to this, and this is a sigma model from a 2-dimensional manifold to this, and so forth. So there are symplectic supermanifolds. Supermanifolds. NQ of weight n. And the question is, what is the geometric gadget here? I have no clue. More interesting is this. Poisson vertex algebras were classical limits of vertex algebras. Vertex algebras, we believe them to be connected to conformal field theories. Those are theories in dimension 2. And I'm telling you that this guy here is the target of a field theory in dimension 3. And indeed, the only example that we can say something is take the Courent sigma model for just a Lie algebra, a Courent algebroid where O is just the field, is the same thing as a Lie algebra with a quadratic form. And to those things, you can do two things. You can take the affine Kac-Moody vertex algebra, take the associated, the graded limit of that, and that's a Poisson vertex algebra, or you can take Terence-Simons, and you get this. So you have a two-dimensional field theory and a 3-dimensional field theory that sit on the same row of this table. So what is that follows here? So I have no clue. But along these lines, what are non-commutative versions of this? Here we have non-commutative versions, and here too. We can look at associative algebras. So if this was classical mechanics, I would think of this as quantum mechanics, and this would be a quantization of whatever this, of the AKSZ model. And here I can look at vertex algebras. Now this quantizing Poisson algebras is an interesting problem, and it's a very difficult problem, but we know lots of things. Quantizing Poisson vertex algebras, there's no such a thing. So first of all, these are not arbitrary Poisson vertex algebras. They come in from Courent Dorfmen algebras, and this is a theorem of Malikov. So this is Malikov. Actually, I think this I should put Gorbunov. Malikov. And Shechtman. Also Beilinson and Dreyfeld. So if you start with a Courent Dorfmen algebra, so this is a Courent Dorfmen algebra, you construct the Poisson vertex algebra associated to that, then there's an obstruction. An obstruction, which is a topological obstruction on this pair. So it's a characteristic class of this pair that you compute, and if it's non-zero, then this doesn't exist. An abstraction to constructing a vertex algebra V such that your PVA is the associated gradient of V. Quantizing that. So these things are known as Gerbs of chiral differential operators. Okay, so this does not happen for Lie algebroids. If you have a Lie algebroid, there is always an associative algebra that quantizes the symmetric algebra of your Lie algebroid. So if you have a Lie algebroid, there is always a sheaf of differential operators for that Lie algebroid. There's always the universal enveloping algebra of your Lie algebroid. So going from the first row to the second row, we lost the ability of quantizing these things. Okay, so that's not a way of doing non-commutative things. So now in the last 10 minutes, I'm going to tell you what we did. One way of finding non-commutative versions of the second row. And here's where this is going to be very fast, 10 minutes. So the work that we're doing with Luis Alvarez Consul and David Fernandez is construct a non-commutative version and prove the equivalence of the second row. And for it not to be an empty theorem, the point is that both of these sides have natural definitions. Actually, both of these sides were already in the literature, plus double, so most of the non-commutative version of these are in the literature. I'm going to be talking about double Poisson vertex algebras and doubly or bisymplectic symplectic manifolds. But I'm only going to concentrate on the Courent Dorfmen side. Okay. So CAGs, I think the order is different again. I don't know. Apparently, I don't know alphabetical order. So De Sole, CAGs, and Valeri, following work of Michel van den Berg. So this, he defined double Poisson algebras. And these guys defined double Poisson vertex algebras. Let me tell you what are the ingredients of those constructions. That was too slow. So everything is going to be non-commutative now. So I'm going to have a base algebra R, might be non-commutative. This is over a field K, so everything is relative to R. A is going to be just an associative algebra. So it doesn't need to be commutative. And I want to construct a Poisson bracket for that A, but instead of landing in A, it's going to land in A tensor A. So this is going to grab A and B, and it's going to land in. So I'm going to write this double guy like this. And we can use the following notation. Let's say that this is A, B prime tensor. And of course, there's a sum implicit in this notation. Okay, so I will require that this operation is skew symmetric, but now this guy lands in A tensor A. I'm going to add the minus just as usual for skew symmetric brackets. But since this is in A tensor A, I'm going to exchange the two factors. So this operation sigma is the automorphism of A tensor A that exchanges two factors. So that's Skew symmetry. I'm going to ask the Leibniz rule is that this guy here is a derivation. So this is a map from A to A tensor A. This is an A bimodule now. A is associative. It's no longer commutative. So it's tricky to talk about derivations of associative algebras. So this is a derivation with coefficients in this bimodule, in this A bimodule. Explicitly, this means, well, what do you think? What do you think it means? Bracket B times C is this guy here, A, B, times C, and this C is multiplying on the second factor of this bracket, plus B times AC. And now this B is multiplying in the first guy in this bracket. So that's the Leibniz rule, and that's Skew symmetry. The Jacobi condition is hard to write. I think I'm going to just exactly finish with the statement and a proof. The Jacobi condition is very hard to write. The Jacobi condition is that, well, let's take A, and we will take the bracket with B and C. And this already includes something. So this guy is it has two factors. Let's say this is D tensor E. So now I need to define what is this bracket. And I can take the bracket of A with D or of A with E. I get to choose them. So I'm going to write here an L, and this means that I'm taking the bracket of A with D. And then tensoring with E. So this is just this L here. I'm taking the bracket with the left guy. So this should be the bracket of A with B and C. And now again, I need to tell you what this guy is. I'm going to put an L there. But this is different now. That's the bracket of something that, let's say that A with B is something of the form D tensor E. And now I'm taking the bracket with C. And I'm saying that C is taking the bracket with D because it's on the left. So this is DC tensor E. But now this is in A tensor A. So let's say that this is F tensor G. I'm going to put a 1 here, and that 1 here means skip the first factor. So this is F tensor E tensor G. So that's the difference between this bracket and this bracket. I'm putting this C in the second, I'm putting this B back in the second position, which is where it was. And then the last one is A. I have 2 minutes. There's no way I'm going to finish in time. A bracket B. C. No, that's wrong. B. B bracket AC. And this is on the right, meaning that this B is taking the bracket on the right. So if this is F tensor G, and I'm taking the bracket of B with that, I'm going to write F tensor B G. So that's the Jacobi condition. An algebra, A, an associative algebra, with a bracket that satisfies this Skew symmetry, the Leibniz rule, and that Jacobi condition is a double Poisson algebra. And an example of such an algebra, let me give you the example, and I'll essentially stop. I'm going to just mention what an example of the Solly and Barreri and our theorem. So an example of this algebra is this. Instead of looking at derivations from A to A, was the case of derivations of O, I'm going to look at derivations with values in this bimodule. So these are called double derivations of an algebra A. And the statement is that if you take the tensor algebra of this guy, in as much as derivations were a Lie algebra, the double derivations have a natural bracket. When you look at double derivations and you write the obvious formula of composing in one way minus composing in the other way, you're going to end up with a double bracket. So this guy has a double bracket. is a canonical double Poisson algebra of degree -1. So this is the analog of the exterior algebra of polyvector fields. I'm sorry. Sorry? This tensor algebra is over K. And okay, so I'm not going to have time for this, so I'm just going to say what the ingredients are and what the theorem is, and I'll stop. So Cax, De Sole, Cax, and Valeri, they naturally define a structure that is exactly what you're guessing that it should be for a double Poisson algebra. So what they say is, you grab up an associative algebra. What is the extra datum that you need? You need a derivation. And now the bracket, instead of being a bracket, is going to be a lambda bracket that is going to go from A tensor A to A tensor A, polynomials in lambda. And then you modify the Jacobi condition so that you have lambdas. So let me write them. And it looks exactly like the usual lambda bracket for Lie conformal algebra. So that's why it's not so hard to come by with. And here, this looks the same. Just you put minus lambda minus del, and you keep the sigma. And here is exactly the same. This is lambda, lambda, lambda. And that's a double Poisson algebra. And the statement is that, so that's one example. So that's just a definition. Now, there is a definition of a Courent-Dorfman, of a double Courent-Dorfman algebra. Dorfman algebra. Let me tell you what that is. This is going to be now an associative algebra instead of a commutative algebra. This is going to be a bimodule, so this is associative. This is a bimodule. And you have the same data that you had before. So this is a module, this is a bimodule over O. Now I want to have the action. So I would want to have a double bracket to E tensor E. Well, actually, the double bracket lands here. So this is the double bracket. That's why you need to take the tensor algebra of derivations. If I only take derivations, that doesn't have a Lie bracket. The tensor algebra does. And that's why you have these factors of O here. And you have a pairing. Which is symmetric. This satisfies the same actions as the Current Orthogonal algebra. This is like a Lie bracket. It satisfies the same skew symmetric and Jacobi condition that has one. And this pairing is invariant for these modulo derivations. So the theorem is these two things are equivalent, and moreover, the canonical example is the following, is that if you have an associative algebra O, is associative, you look at double derivations of O. So these are derivations from O to O tensor O, and you sum its dual, which is scalar differentials on O. Then this thing here is a Courent-Dorfman algebra over O in a canonical way. Yeah, so I'm sorry I took so long on the classical picture. But the theorem is that these two things are equivalent. If you start with a Cax, De Sole, and Valeri double Poisson vertex algebra, you look at what happens in degree 0, and you look at what happens in degree 1, and you get this datum that was known to be the datum that you need to construct these bisymplectic manifolds. So that's one way of getting non-commutative versions of extensions of this table that we had here. I have no clue what the physics behind any of this would be, if there's any physics behind that. I'm sorry that I'm over time. Too much time on basic stuff.
Any questions or comment? Can you define double vertex algebra?
No. No one knows.
So this is a sheaf on a non-commutative.
Yes. So that we do know. So you can ask it to be local. So we've proven something more. This is more the work of my collaborators, actually, not mine. But they've proven that that this current Dorfmen example satisfies what's known as the Reutenberg, the Kontsevich-Reutenberg principle. So that you can think of it as a geometric picture. And indeed, you can shapify. This is local in nature. All of this construction is local in nature. It's local overall.
Any other question? So if not, let's thank the speaker. And we resume in 7 minutes.